I will quickly give the floor to Dr. Ayman Sob, who will introduce today's talk. Dr. Ayman Sob is the president of Al-Aqsa University. Dr. Ayman, the floor is yours.
Okay, thank you very much, Dr. Christine. Ladies and gentlemen, distinguished guests, esteemed colleagues, and curious minds, good afternoon, and welcome to this distinguished scientific event, a gathering dedicated to the pursuit of knowledge, wishing you all the best. It is a true honor to stand before you today as we open this exciting session in scientific exploration and collaboration. It is with great pride we at Al-Aqsa University continue holding a distinguished series of excellence lectures across various scientific disciplines. This initiative started at May 2025 as a joint effort between Al-Aqsa University and the Academic Solidarity with Palestine. It features several prominent scientists in the fields of physics, astrophysics, and mathematics. Al-Aqsa University is an independent governmental university, Palestinian university. In fact, it is the largest governmental university in Palestine, established in Gaza in 1955 as a teacher training center. It officially gained university status in 2001. The university's mission is to graduate a generation equipped with knowledge, values, and skills within a modern educational environment that incorporates technology, scientific research, and community service. Today, the university serves over 25,000 students across 4 main campuses. It employs more than 500 faculty members and 600 administrative staff, and comprises 12 academic faculties offering programs in science, engineering, education, media, law, IT, medical sciences, and other disciplines, including Al-Aqsa Community College for Intermediate Studies. It is with a great pride, ladies and gentlemen, despite the difficult circumstances that Palestinian universities in the Gaza Strip are currently enduring, the journey of education has not stopped. At Al-Aqsa University, we remain committed to delivering education through e-learning platforms and to sustaining scientific research to the best of our ability. These webinars are conceived as a way to inspire academic engagement, support ongoing research efforts, and revive hope in the hearts of students and scholars in Gaza. Even in the face of war and destruction, we believe that knowledge and learning can light the way forward. Today, it is my pleasure to introduce Professor Cedric Villani, the famous mathematician known for his work in partial differential equations, Riemannian geometry, and mathematical physics. Professor Villani received the Fields Medal in 2010 and has also been awarded the Henry Poincaré Prize, Fermat Prize, and the European Mathematical Society Prize. He served as director of the Institute of Henry Poincaré through the interval 2009 to 2017 and has been a professor at ENS Lyon since 2000 and at the Institut des Arts et Études Scientifiques since 2022.
Hello, hello. Should I start?
Closing.
Oh,
In closing, I'd like to thank the Deanship of International Relations and the Deanship of Scientific Research at Al-Aqsa University, especially Dr. Radwan Abu Rukba and Dr. Hazim Abu Shawish, as well as the academic solidarity with Palestine, especially Dr. Christine and Dr. Saida from Al-Najah University, for organizing these webinars. I also extend my thanks to the speakers and participants for their valuable contributions. I wish you all an engaging and successful event. Thank you for being part of this meaningful journey.
Thank you so much, Dr. Ayman. It's such powerful message.
Thanks for you.
Thank you. Cédric, the floor is yours since Dr. Ayman has introduced you beautifully. So it's now you.
thank you so much, Anne-Christine. Thank you, Dr. Ayman, for the very kind introduction. 14 years ago, actually, I was lecturing in Palestine in a tour together with my colleague Etienne Gis, now the Secretary Perpetual of the Academy of Sciences, and Idriss Titi from Weizmann Institute. And we made this tour in Palestinian universities, in particular Naples, Ramallah, Al-Quds. It is my pleasure here today to be part, even in such difficult circumstances, to this series of lectures organized by Al-Aqsa. My friends, I will give my lecture on one of the most famous episodes and themes of mathematical physics. Mathematical physics is the science of studying using mathematical tools to study physical phenomena, with two main issues. The first is about finding rigorous justification of some of the tricks and tools that the physicists have. And the other is finding new justifications, new tools, new ideas, new relations that the physics approach will not be able to derive on its own. One of the most famous mathematical physicists of all times was Ludwig Boltzmann. And I consider myself a true heir of his in many ways. And the story I will tell about is in large part the story initiated by Boltzmann. This was an amazing scientific revolution which took part at the end of the 19th century. The two big names initiated it were, on the one hand, James Clerk Maxwell, and on the other hand, Ludwig Boltzmann. They were such very different persons in terms of character. Maxwell was very shy to the point of barely being able to teach to students. And Boltzmann was very much full of energy, coming and shouting on the scene like an actor when he was doing his lectures, which were like plays and which were attracting many people. Maxwell was the first one to tackle the problem of putting statistics into the idea of atomic theory. Atomistic theory was born several times in the course of history of sciences, but the main moment where it really started to be quantitative and mathematically studiable and feasible was after 1850, when Rudolf Clausius in Germany started to put thermodynamics on the foundations of the atomic idea. And Clausius introduced very important ideas, such as this idea that the matter around us is made of small molecules bumping onto each other, that typical important quantities are the time it takes between two particles to collide, and that this would explain many properties of gas, like pressure, like velocity, temperature, etc., etc. And Clausius was a great physicist, but not such a great mathematician. Maxwell took up the problem again, was fascinated by it, young at the time, and knew much more mathematics and understood that to make sense of Clausius' ideas, you needed to put statistics in there. Maxwell was very much influenced by the development of human statistics. In those days, the artists of statistics like Kettery and the others had shown how in social sciences, you found all kinds of statistics that are possible, and the presence everywhere of the famous Gaussian profile, the exponential minus x squared or something like this typical error curve that you can find everywhere. And Maxwell put statistics in the Clausius picture and discovered the first version of what we now call Boltzmann equation. Maxwell was the only one to be able to follow the complexity of putting together the statistics and the physics. And Boltzmann took it again, and for some time they were doing some kind of ping-pong match. Maxwell improving the ideas of Boltzmann, Boltzmann improving the ideas of Maxwell, to the point where around 1870s, Boltzmann gave the theory kind of the form that we know now. I will write for you what we call the Boltzmann equation, explain what it represents, and why so many things started from this. So the two big papers of Boltzmann are 1865 and 72, and here is the Boltzmann equation. df dt plus v grad xf equals q. What does it mean? This is a partial differential equation. As Dr. Ayman rightly said, I am known for my work at the interface between partial differential equations and geometry and statistics. And f here is the unknown. F depends on time, it depends on position, it depends on velocity. Velocity is the new variable that Boltzmann and Maxwell added, and that's why this whole game is called kinetic theory, kinetic for velocity. T is our time, x is the position, and it is assumed that all around in matter, say in a gas, there are a lot of small molecules, and F tells you at time t, which is the density in the space of positions and velocities, so in the physical phase space for these particles, the physical density for these molecules. So it's a time-dependent probability distribution in 6 variables, 3 for x, 3 for v. Later, I will sometimes put less or more dimensions. You can set the problem in 2 dimensions, 4, 5, 6, whatever dimensions you like. But the most important and the initial physical problem is when there is these 3 dimensions. This is the gradient respect to the x variable. I put here gradient respect to x variable. It's the variation of the density f respect to the x variable. This is v, so you take the scalar product of v with the gradient in x of the f distribution. And this term is here to say that particles typically go in straight lines before they collide. This is just the Newton's law, if we wish, the Galilean usual invariance. So particles without any force, it will just go in a straight line. And this here is to tell the effect of collisions. When 2 particles collide, 2 velocities disappear, the velocities before the shock, 2 velocities appear, the velocities after the shock. Because this is about binary collisions, and the gas is supposed dilute enough that more than collisions involving more than 2 particles are negligible, the operator Q is quadratic. Q takes this form, integral over R3, integral over the sphere of f prime star minus f star, and here it's multiplied by a factor b. Here, this means we are integrating among all possible velocities of particles which will come and collide you. If you are a particle with velocity v and you ask which are all the other possible particles that will come and collide you, and this is your velocity v, this is the other velocity v star that will come. So the integral will be over dv star and d sigma. And this parameter sigma here is to tell you about the possible configurations of the shock, the geometric configurations. You see, if the particles are like this, or like this, or like this, the output will not be the same. Or maybe these forces are not really collisions like Hart spheres, but maybe these are inverse power forces or long-range forces. So collision will be something looking like this, you see? Particles coming closer and then getting out. And then whether at minimum distance they are like this or like this or like this or like this, the output will be different. And this we take as an extra parameter that is this sigma. And F is like the value of the density function at time t, position x, velocity v. F star is at velocity v star, the particle which comes to collide you. Now F prime means F prime and F prime star are the values of the distribution function when after the collisions, and now the velocities after collision are v prime star. Here is a picture of the collisions. And let me insist, this picture in itself is coming only from classical mechanics. It's one of these problems. You are solving a problem of scattering and counter between particles. So here, this is V. This is V star. This is V prime. This is V prime star. This is the velocity we're interested in. This is the colliding particle. And this is before the shock. These ones are after the shock. I will write sigma for this direction. I will write k for that direction. And between k and sigma, there is a certain angle that is a deviation angle, theta, say between 0 and pi. And you see here, they are the corresponding geometry of the shocks. These are elastic collisions. It's a different story to put inelastic collisions. This is the Boltzmann sphere, as we call it. And the game that Maxwell and Boltzmann played was, let's assume that particles do like this, these interaction, these collisions, and what will occur? How will the properties of the equation be affected? I did not tell you what was the factor b, which I put in front of the integral. B is here to tell you about the respective occurrence of parameter theta. Maybe if it is Hart sphere, so collisions are like this, pack, it will not be the same distributions of angles after collisions than if it is, say, Coulomb potential with very long range interaction. And actually, Maxwell himself did the computation in a very clever and powerful way to say, assume that the forces are like 1 over r to the s. This means that two particles at a distance r will interact, attract each other, or repel each other, doesn't matter actually, will repel each other with a force that is proportional to the inverse of r to the power s. What will be the factor b like? And the answer is b will be like a power of the relative velocity, v minus v star, multiplied by a function of the cosine of the deviation angle. And Maxwell gives the computation of these things. He computes gamma. Gamma will actually be equal to s minus 5 divided by s minus 1. This will be gamma. And cos theta is not explicit, but is given by solving some equation involving an integral, and it's a transcendental function that is hidden behind. And he computes the behavior. And for an inverse power force like this, there will be a strong singularity at theta equals 0. It will be strongly non-integrable at theta equals 0, showing the fact that collisions with very, very small deviation are very, very numerous when the forces are long range. Now, this, I told you, is the equation of Boltzmann, and I will rewrite the equation here and explain you why it was so important and what one would like to do with it. And let me say right from the start, this equation is more than 150 years old. However, the biggest mysteries on this equation are still open. So let's write the equation again. Df dt plus v grad xf equals q. And let me write it q of ff since it's a quadratic. So this was 1872 in this form. It was a monster progress in many respects, especially after Boltzmann introduced and proved his most famous result known as the H theorem. H is this functional for Boltzmann, double integral of f log f dx dv. And Boltzmann first relates this to the fact that the distribution function is rare or common. A distribution function is common if there are many ways to realize it using microscopic fine-tuning of the molecules. A distribution is rare if it is very difficult to realize it. Imagine the particles, the states of particles like small boxes, and imagine that you know that statistically only box number 1 is represented. Then this gives you only one choice for putting the molecules all in the same state. On the other hand, if you know that all boxes are equally represented statistically, you have many, many choices. You can put one here, there, etc., etc. So the second distribution is much more common. And the value of H is a way to tell which distributions are rare, which distributions are common. H is the negative of what would be called the entropy of Boltzmann. And Boltzmann shows three amazing things. First, he shows that this quantity along the equation always goes down with time, which introduces an arrow of time, even though the underlying dynamics of Newton is time reversible. So first thing, H goes down in time. Second thing, he shows that the only possibility that the information does not go down is when it is minimum, and that this can occur only for a Gaussian distribution with this velocity of profiles for the velocities, this profile for the velocities. In a box, it will be homogeneous in space and Gaussian in velocities. So this is amazing because that distribution coming from the central limit theorem, from Gaussian fluctuation, we learn at school about this, which is probably the most famous, single most famous theorem in mathematics, the law of errors. This appears spontaneously in this problem coming from the laws of Newton and the statistics. And third thing, when the gas is not at full equilibrium, but when it is an equilibrium only in the velocity variable, and that density, temperature, and velocities, macroscopic velocities are still allowed to vary. So when we reduce the kinetic description into usual fluid description, the fluid is determined by density, velocity of the fluid, and temperature of the fluid, then the formula for H goes down, reduces to the formula for the negative of the entropy of fluids. So making a connection between the description of kinetics and the usual description of fluids. This was opening an enormous world. From the point of view of mathematics, it was the first time that there was such an equation with a distinguished Lyapunov functional, as we call them now, indicating a global and universal behavior. Now there are so many, but in those days it was the first time. From the physical point of view, it was showing that an arrow of time was compatible with the microscopic reversibility, and that this could be explained from a statistical point of view. In those days, Boltzmann was the only one to understand this. Even Maxwell was lost at this point. You see, the laws of thermodynamics was something like entropy should always increase, second law of thermodynamics, as we call it, and learn it also in class of thermodynamics. And people thought of this as a law which is absolute. How could an absolute law be resting on something that is statistics? If it is statistical, it will have random fluctuations. it seemed to be some absurdity here. And Boltzmann rightly explained that this is due to the orders of magnitude. I will come back to this. But then this was also the birth of what would later be the theory of information, a field that would grow and grow all throughout the 20th century, in particular for the theory of communication. Shannon found the same formula of Boltzmann independently when he wanted to understand what is the capacity of a transmission channel when you have a signal that you want to transmit. And this was one of the pillars of the revolution of telecommunications in the 20th century. And other people came later, people like Kolmogorov, Sinai, Chaitin, and others, to say what is the notion of information and how can we develop this most important notion from physics, something like the other pillar of physics. On the one hand, there is matter and energy. On the other hand, there is information and complexity. And the development of this, the huge development, blossoming of this is one of the key scientific facts of 20th century, recently renewed by quantum information theory and so on. So this was an amazing achievement, and it would start an extraordinary amount of speculation and problems and issues. The most famous problem of all starting was the following, the approximation problem. If you start from Bohr's enjoying the dynamics of Newton, and you want to do the kinetics of it, the statistics of it, and you want it to be to transform into the Boltzmann equation, how do you do it? So picture this in your head. On the one hand, you have this huge billiard in which many particles and particles collide, and it's colliding again all the time. And on the other hand, you take a statistical description. So you take 1 over n sum of Dirac masses xi dot. This gives you a density, a distribution function on the phase space. It tells you how much mass there is in phase space, x and v. And you ask whether in the limit, when n goes to infinity, this thing here converges to the solution of the Boltzmann equation. It's a theorem of the form of a law of large numbers. You know, law of large numbers, you take the empirical distribution and you ask whether as n goes to infinity, it converges to a certain given law. And we know that the key for the law of large numbers is the independence. Particles cannot be independent. They are all colliding, so there's a lot of correlations. But Boltzmann argued that at first there should be some kind of independence, and he gives reason for this. And that even this, when two particles collide, they don't know each other beforehand. This is called the initial chaos, or Stoßzahlensatz in German. Then after collision, they will be correlated because they have met. But further collisions coming from other particles will immediately destroy these correlations very quickly so that they will remain kind of uncorrelated. This is the central argument of the so-called propagation of chaos. Is it valid or not mathematically? It has been 150 years of discussions about it, and we still don't know. However, there was partial progress, and it was each time there was some progress made, it was a landmark. The most important result to make the theory of Boltzmann plausible and this propagation of chaos was obtained in 1973 by Oscar Lanford. Oscar Lanford proved the Boltzmann approximation and proved that chaos approximation, but only on a very small time interval, a time interval which is of the same order of magnitude as the typical time between two collisions. This means for the gas around us, something like 1/1000th of second, like 10 to the -9. This is amazingly small, and we are not satisfied with it. We would like it to be like minutes, or at least seconds for it to be physically meaningful. For the moment, we have 1/1000th of second. However, it is certainly the most important mathematical theorem in the field, showing that it's not absurd to have this going from the vision of Newton with very many particles to the Boltzmann distribution, to the Boltzmann picture. There are actually three main topics, three main mathematical ways to attack the problem set by Boltzmann. So the first I told you is n goes to infinity. When the number of particles goes to infinity, are you able to prove the deterministic limit? And I told you it's like a law of large numbers, and the main result is Langford 1973. I should have added that it took more than 40 years before the theorem of Langford was fully proved. Actually, there were mistakes in the proof. It was later repaired, and there were mistakes in the repair. It was repaired again, etc. And finally, there were the results very clearly established by the team of Saint-Rémond and Gallagher and Bodino and Texier. It was about 10 years ago. I taught it at university in class, and I went through hell. This is extremely difficult stuff. Very important, as I told you, however. The other possibility, if you fix the number of particles to be n fixed, and you do t goes to infinity, that is related to a completely different field of mathematical physics named ergodic theory. In particular, you'd like to know if, as time goes to infinity, the particles in your box, the configuration, goes through every possible configuration that is possible. This was the birth of ergodic theory, which took a life on its own, and it's extremely important field of mathematics in general now, but which appeared to be deceptive for the Boltzmann theory. Boltzmann himself put it in the game, but that, I believe, was a mistake. This is not the relevant limit when you want to study it, and most of the work of Boltzmann rather had to do with that limit. For balls and gas of Boltzmann, the problem of ergodicity was solved by Shimony about 20 years ago. And there are still some reasons why we should not be completely satisfied with the proof, but anyway. But now, what you would really like to do is first let n go to infinity, and after you've done n go to infinity, you are at the PDE level, and then you'd like to let t go to infinity. That is the thing that makes physically most sense, and mathematically as well, which goes through the study of the partial differential equation. Most of my work was related to the PDE itself and the limit t goes to infinity for the Boltzmann equation. I never addressed that one, or only for baby simplified models. What I was able to prove, you kindly mentioned the Fields Medal, which I obtained in 2010, is in particular related with the works with my collaborators, Laurent Devillette on the one hand, Clément Mou on the other hand, to consider the partial differential equation and study the limit t goes to infinity, and show for the full collisional Boltzmann equation that if there are regularity bounds on the partial differential equations, then we can prove the whole limit t goes to infinity, convergence to a global Maxwellian, and have control on this quantitatively. And on the other hand, to show that there are no collisions, that is, for instance, for Coulomb gas, in which there are hardly any collisions, show the limit t goes to infinity through averaging techniques in some special cases in the regime called the Landau damping, near homogeneous equilibrium. Let me say that each of these three boxes, n goes to infinity, the PDE itself, and t goes to infinity, are three enormous sectors on its own on which you can make your career nowadays in each of these sectors, and each of them is hundreds of papers and will be hundreds of more papers before we understand. It's not one of these problems where you say, okay, I have the proof and that's the reason why. It's one of these in which you need enormous amount of information scattered in various ways to do things, improvements, etc., etc. The theory of that Boltzmann equation now is several thousand papers, and I myself wrote a survey paper of the mathematical theory of it at the beginning of the 2000s, and recently I wrote a kind of survey that you may consult on Archive. If you go to the Archive website and search for my recent publications, we'll find one lecture notes, which is the course which I gave. It's called Fisher Information Estimates in Kinetic Theory, which includes something like a review of the mathematical theory of the Boltzmann equation. Let me, rather than giving you the whole picture, focus on one small subset of this, explain you why it's dear to me, and why there was recent progress in it recently. I told you about the limit n goes to infinity, the PDE, the t goes to infinity. In my view, and I was trained as an analyst and specialist of PDEs, the central is this one. When we know how to control this one, not only are we able to do this one, but also we have new tools and ideas to understand this one. Very often, knowing the limit and knowing very well the limit gives you clues and ideas about the way to approach. And let me explain you what is this subfield and subset that I was telling you about. So it's about the partial differential equation. In the simplest case, when you don't have anymore the dependence on the space, but only the dependence on the velocity. So the equation becomes df dt equals q of ff. That is the spatially homogeneous Boltzmann equation. The mathematical theory of that equation was started by the Swedish analyst Torsten Kahneman in the 1920s. And an important paper he published in this in 1933 for hard spheres. And even though it is that old, it's only recently that the theory of that equation, very much simplified by the assumption of spatial homogeneity, was completed. Indeed, there was until recently, a certain class of interactions that we, experts in the field, were unable to address. Remember, when I gave you the form of the integral factor b, I told you it's the power of v minus v star multiplied by the function of cos theta. And we were stuck when the power gamma was too negative. In particular, we were stuck for an important case of application when you want to handle collisions related to Coulomb interaction. Then in dimension 3, gamma equals -3. And b of cos theta, when you look at b of cos theta, and you look at the multiplied by sine theta, which is the Jacobian of the spherical change of variable in dimension 3. This was like theta to the -3 as theta goes to 0. And singularity here is very large, but the negative power here is very large. And for those reasons, we were unable to find a good theory of solutions. In my PhD, at the end of the 90s, I had constructed the first weak solutions for this equation. Weak solution is when you don't have a regularity estimate, and for certain amount of purposes and goals, it was okay. But for other purposes, you'd like to know how much is the regularity, and it was a very embarrassing open problem to know whether there were regularity or not for these equations. For when gamma is equal to -3, or for a whole class of negative powers gamma corresponding to what I had called very soft potentials. The problem stood wide open for more than 25 years. And there was another problem on which I had worked, but which itself seemed to be closed and solved on the other hand. And this other problem was the following. It was doing some information theory estimates for the Boltzmann equation and study another quantity than h, quantity which is known as the Fisher information, integral of grad f square divided by f dv. This quantity here appeared in the work of Fisher in the 1920s. Fisher was probably the most famous statistician of all times and introduced this quantity to quantify how much information there is in a distribution function. When you're doing statistics, trying to observe an unknown distribution function, you want to reconstruct the distribution function. Is it easy or not, and is there a lot of information in each observation or not? This is what tells you whether there is a lot. And if the information is very high, it means that you will easily reconstruct the profile. And if the information is low, you'll have a hard time reconstructing the profile. Fisher information is very well known to statisticians and specialists of information theory. Even in quantum computing, it plays an important role. And Fisher information is related to the information of Boltzmann in many respects. First, because you can go from one to the other by differentiating along the heat equation, that one. And second, because they are related in the same sense that volume is related to surface. In a way, when you are observing objects in space, etc., you want to say how large they are. There is the intrinsic notion of volume, which tells you how some object is large. And there is the extrinsic notion of surface, which is how I can observe it from the outside. So this would be the volume, this would be the surface. And there is an analogy between them, which is so strong that it was exploited by Dan Voiculescu to give some very fascinating proof of the main inequalities about Boltzmann information called the Shannon-Stam inequalities using this analogy in infinite dimensions of volume and surface. So they are related in many respects. And also there is a whole kind of differential inequalities known as the theory of logarithmic Sobolev inequalities, which relates both. For instance, so remember H is integral f log f. For instance, if I look at distribution functions on the sphere in dimension d, then I know that H will be bounded above by 1 over 2k times I on the sphere. And this k here, which will be the logarithmic Sobolev constant, this is what is called the logarithmic Sobolev inequality, the fact that for any f, you have this. And the k here, the optimal k here, will be equal exactly to d minus 1. And exactly to d minus 1. And there is a whole theory about this and books about that. In particular, I recommend the book by Bakri, Gentil, and Ledoux, showing how it's related to a number of problems in the theory of diffusion equations and problems of concentration of measure and problems of classical Sobolev inequalities, etc. And so they are both related, and it's part of a big game. And it was interesting to see how this quantity relates to the Boltzmann equation. The first who had the idea to do this was Henry McKean in the 1960s, specialist of stochastic processes, extraordinarily inventive mathematician. And Henry McKean showed that the function I goes down for a 1D caricature of Boltzmann equation. I write 1D Boltzmann without stating precisely what it is. And he had used the fact that this goes down to give the first proof of explicit convergence to equilibrium for that one-dimensional Boltzmann equation. Explicit convergence to equilibrium without linearization. In the 90s, Giuseppe Toscani, so this was McKean, the first result. Then Toscani showed that for the Boltzmann equation in 2D, if for the Boltzmann equation in 2D, and if gamma equals 0, you remember gamma is the power of V minus V star in the collision kernel B, then it's also decreasing. And in my PhD, I had shown that it's true for any dimension if gamma equals 0. And I was happy with this because there was good parallel with the theory of information, classical information theory, etc., etc. And it was kind of moral because when gamma equals 0, there are a lot more properties with the equation. Some coefficients are simpler, etc. Maxwell himself had noted that when gamma equals 0, things go simpler, and that's why they are called Maxwellian molecules. These when there is this interaction. I was happy with this, and I was damn wrong. And I should have listened to people in those days at the end of the 90s who were running numerical simulations and told me even when gamma is not equal 0, we see that it seems to go down numerically. I was not convinced that by them because I thought, this is numerical simulation. It's difficult to see and whether it's really the truth. And anyway, we know that the minimum is for the equilibrium distribution, so maybe it's an artifact. But I was damn wrong because the fact that I did not listen to it prevented me from searching harder on generalization on this. And then it came as a slap in my face when 2 years ago, Nestor Guillen and this was Nestor Guillen and Louis Sylvestre, two young mathematicians, a bit younger than me. Actually, I was the one who had suggested to Sylvestre long ago to start and go adapt his methods to the theory of Boltzmann equation, prove that for the particular case of the plasma physics equation, it was indeed going down in any dimension. And this was like a wake up for me. I jumped back in the field again, went back to my old papers from the time of my PhD, more than 25 years ago, to be in the bath again, refine the theory, rerun the computations, and join forces with Louis Sylvestre and also with French mathematician Cyril Imbert so that we could prove the general case for any D and for any gamma. This we proved, it was last year. And the preprint, which I told you, which is on the archive, you will find it with the proof and the long proof and how it's related to a number of problems. Let me first notice this. So look at this remarkable fact. What we prove is that when you forget about the spatial dependence and look only at the velocity distributions, velocity dependence, so the effect of collisions, the Fisher information goes down. Before that, it was only known that the Boltzmann information go down. Isn't that amazing? The equation is 150 years old, and we are still discovering new general Lyapunov functionals. And not one that is ad hoc and created from scratch with some complicated formula. A Lyapunov functional whose form is known for 100 years, which has physical meaning, statistical meaning. Fisher information tells you whether a distribution is easy or not to reconstruct, to observe. So it's a complement to the Boltzmann information, which tells you if an information is rare or not. So this tells us something. Collisions somehow make the distribution function more and more difficult to observe and to reconstruct. It has to have some physical meaning and consequences. I am not sure exactly which ones, but you have here a simple statement, general, on quantities which are meaningful. Actually, there have been some attempts over the past decades to build thermodynamics on not just the Boltzmann entropy, but also the Fisher information. And this gives new fuel and new motivation for pursuing that goal and pursuing those researches. Then, from the mathematical perspective, the first thing is, this gives, as we say in partial differential equation, a new a priori estimates. Fisher information is the same as 4 times the integral of the gradient of the square root of f to the square. It's just a way of rewriting it using the chain rule. So if Fisher information goes down, it means that automatically you have an a priori estimate on the regularity of square root of f. Namely, the gradient of the square root of f is square integrable, and that is a regularity estimate. Actually sufficient to prevent the blow up and to control the equation and to solve the regularity of the Boltzmann equation in all the remaining cases which were open. So that quest, which was like open for about 30 years, was solved thanks to that new estimate. And of course, giving you new tools and new hopes for the generalization of the theory. This is all for the spatially homogeneous, which is the first step to the general inhomogeneous. And then, from the mathematical point of view, also the way it was solved is by establishing connections, deeper connections between the branch of kinetic theory on the one hand, and the other branch, which is the theory of logarithmic Sobolev inequalities. I worked in this field for years and years and years, but still I was not prepared for the kind of connection that we discovered and that I will explain you here. So remember the Boltzmann collision kernel, write it like this, V minus V star square, B of cos theta. Okay. Now, if our theorem says this, if for any f from SD minus 1 to R plus, and actually not exactly SD minus 1, even function on SD minus 1, which means quotiented by plus minus identity. In pedantic terms, this is the projective space of dimension D minus 1, the real projective space. In pedestrian terms, it's just functions on the sphere valued in R plus, which are even. That is, if you change x into minus x on the sphere, then you don't change the value of the function. If you have this, so for any f, integral of square root f of k minus square root f of sigma square b of k dot sigma dk d sigma, so it's a double integral on the sphere. If it's less than 1 over k times the double integral of f of k grad log f of k minus grad log f of sigma square, and similarly here with the b and dk d sigma. And there is a little twist. I will explain very shortly the little twist about this square. If it is like this, for any f, if it is like this for any f, so this is an inequality which here there is a gradient and a log. So it actually looks like it's like a kind of point. It would be a Poincaré type inequality if it would be just gradient of square root f here. Here it's a combination of a Poincaré inequality and the logarithmic Sobolev inequality in a way. So if you have this formula holding for some constant k and for any f, then and the absolute value of gamma is less than square root of k, then I goes down along the Boltzmann equation with time. Look at this. It's the first time in my life in which I see a problem coming in classical mathematical physics in which the range of equation admissible, the range of parameter admissible for the theorem to hold true, depends directly on the value of the optimal constant in a functional inequality. For mathematical completeness, I will tell you which is the twist. There was something like grad something, grad f sigma minus grad fk in the previous blackboard, and I put here a square. Actually, there is a catch here. You have to distort the square norm here using, by definition, y minus x k sigma square is equal to x square plus y square minus 2 p k sigma x scalar product Y, in which pk sigma of x is by definition equals to k dot sigma x plus k dot x sigma, sorry, k dot x sigma minus sigma dot xk. If you wish, in a way, I cannot, thinking geometrically, I cannot directly take the difference of these two gradients, which are gradients at different points on the sphere. I must first transport the gradient at point K to the gradient of point sigma using this transformation, which is a way to map the tangent space at K to the tangent space at sigma. A bit like a connection in Riemannian geometry, much simpler though than the Riemannian connection. I state this for mathematical completeness, so to make sure that what I write here is true, but anyway, on the preprint, which I mentioned to you, and I saw that somebody put it in the chat, you will find all the details and how it is connected. So I did a lot of work in my career on the Boltzmann equation and quite some work also on theory of logarithmic Sobolev equation. For instance, together with Felix Otto, we were the first ones to show that certain inequality of concentration due to Talagrand was automatically implied by the theory of logarithmic Sobolev inequalities, etc. But I never suspected that there was such a deep connection between both. And I never suspected that the problem of solving the Boltzmann equation in the very singular case of very soft potentials was related to the problem of optimal constants. And you see also the interesting lesson in this. The problem was sleeping for more than 25 years. I could possibly have gone to my grave thinking the problem was too hard to solve if it had not been for the wake up and the advance made, to my big surprise, by Guillen and Sylvestre. And this time scale in mathematics, however, is not uncommon. Sometimes 10 years later, 20 years later, 100 times later arrives a new surprise and something gets out of the oblivion. It was not a problem of technique. We had all the technical tools at the time. Okay, actually some of the technique we had to reprove here. For instance, the optimal value, to compute the optimal value is quite an enormous affair, and we had to work out actually some optimal constants in the field of logarithmic Sobolev inequalities on the projective space, which had not been studied by lack of motivation. But we could possibly have written all these papers 20 years ago. All the ingredients were there, but the way to do the computations, the way to see it, the way that this, and that is related to this was missing. And it's somehow reassuring to see that some unexpected, beautiful things are still here to be found, even in fields which have been worked on and worked again and again by many clever people. The nice flowers can still pop up anywhere. Thank you.
Thank you so much, dear Cedric. It was fascinating even for me who doesn't understand much of it. I will now, really wonderful. I will now leave the floor to Karma Dajani and Sharon Fournet, who will choose read the questions from the audience and engage the whole scientific discussion. Thanks again. Sharon and Karma, the floor is yours.
Okay, hi. I got one question, and it's actually also a question of mine. Some elementary references on information theory, Shannon and entropy, and its link with thermodynamical entropy.
There is one very nice book on information theory, which is so nice that everybody has adopted it, by Thomas and Cover. If you search Thomas and Cover, you will find that book that has several editions, and it's really nicely done. And this does the job for information theory, the relation to the large deviation theory, Sanoff theory, etc., in an excellent way, and also some elements about the Shannon theory. If you want to know about Shannon himself, who's a fascinating character, I recommend you take a look, but this is for your culture, at the book which is called The Idea Factory. It's a story of the Bell Labs by science journalist John Gertner. And there is a chapter on Shannon, which is fascinating. And if you're interested in quantum information theory, then there is a book by Huang and Nielsen called Quantum Computing and Quantum Information or something like this, which has become the standard reference for these information issues. And there is also a fascinating book by John Bell, the famous theoretician from the CERN. John Bell with in the re-edition with a foreword by Alain Aspect, which is something like told on untold on the speakable and unspeakable about quantum mechanics or something like this, which is a very fascinating book, even if you don't understand the whole thing. So information is one of the key themes running through physics and mathematics all throughout the end of the 19th century to this day. And as I said, it's like the other pillar. On the one hand, there is a material world with the velocity and the energy and the mass and so on. And on the other hand, there is the complexity and the information and the description, etc., etc. To the list, let me add an elementary reference, which is a book by Chaitin on information. I don't remember the precise title, but it's a very nice broad audience book about information and his dear baby called the Omega number. The relation to thermodynamics, you are telling me also, you are asking me, is not so well covered in the references that I told you. I would rather go for broad audience books on the kinetic theory. The old book by Boltzmann, you know, the Boltzmann wrote a big book which has fascinated people in his generation and later. The mathematical physicist Mark Katz called it one of the most important books ever written in science. And actually it is this book which convinced young Albert Einstein of the existence of atoms, and it is this book that was also the start of the reflection by Erwin Schrödinger, both of them disciples of Boltzmann. And for Boltzmann equation in general, there are there are several books by the late Carlo Cercignani, and one of them called From Basic Concept to Actual Calculations is rather simple.
But I see a lot of similarity actually between Shannon entropy and the entropy you mentioned. I mean, it's the principle of F log F, right? Yeah.
Absolutely, absolutely. The story, Shannon, so you know what Shannon was interested is how much information is there in a language. And the idea, there are several formulations of entropy, like Kolmogorov says, for instance, which is the smallest sentence that can describe your computer program, for instance, or a mathematical result. And Shannon says, how much information is there so that I can compress it to transmit it safely? And Boltzmann says, how rare is the distribution function? And this issue of rarity is the common point. Shannon says, what has value in information is what is rare. If I say a word that is very common, no information. But something that is rare has information. That's the start of his thinking. And then Shannon wanted information to be additive. That is, if I listen to one signal and another signal which is independent, then the two information should add. And from this additivity property comes the log, necessarily. So Shannon finds again the same formula as Boltzmann. And Shannon discusses with John von Neumann in Princeton, and von Neumann tells him, and Shannon wanted to tell it information, like the information content, etc. And von Neumann told him, call it entropy. First, it's already been studied in physics under that name, but since nobody knows what entropy really is, you will always have the advantage on a debate. That was the remark of Nasty von Neumann.
Thank you. Maybe Søren can.
Yes, thank you, Cédric. It was a very wonderful talk. There was a question in the chat that I think is very important to pass on. It's because now you both talked about sort of classical mechanics in some sense, and you also mentioned quantum information. several times. And you've talked about correlations, and so are correlations and entanglement. I mean, what are their relation? I think that's a good question.
It's an enormous subject. In general, entanglement is all about correlation. There are two nice books by two of the recent Nobel Prizes on this. One is by Alain Aspect, and the other is by Anton Zeilinger. Both very good books about popularizing the idea of entanglement. And that's fact which has been proven that there may be particles which are 1 million kilometers away and still be correlated, in the sense that if we do one measurement on this one, then the measurement will give a certain result on the other hand. And it's not information that is pre-recorded. That is not that they were born with an information and carried it all the way. Before you do the measurement, you cannot say that it will be the same on the other hand. That's actually, it's one of the big results of theoretical physics of the past decades, is to show that the combination of causal reality on the one hand and locality on the other hand is false. Either one of them is false. And Einstein considered both to be necessary for any theory to be satisfying, but we know that our world does not satisfy the combination of both. Then there is an issue about which one remains true, and this is other subject of debates, or maybe none of them is true, actually. So the book of Zeilinger and the book of Aspect are excellent Brownian references about this. Now, in general, entanglement is about, indeed, correlation, but there are also correlations and initial correlation in the classical worlds, and let's say that the quantum description adds another possibility of correlation and non-correlation. So in that sense, the quantum nature of the world adds another layer of complexity to the game. And the kind of entanglement or the kind of correlation which is described in the experiences of Clauser, Aspect, and Zeilinger is a different notion of correlation than the classical one. Already the classical one is interesting and meaningful. What I should say also, I told you about the propagation of chaos and told you in classical terms is really the big thing. And the fact that when two particles collide, after that, collisions with other particles will soon destroy this particular correlation with the two particles, so the recollision issue. Of course, in real life, there are quantum fluctuations. And they are important because it's a chaotic system, billiards. So even a tiny fluctuation due to quantum fluctuation, after just a few collisions, after a few classical collisions, will become sufficiently large to be classically measurable. It will become a classical unprecision, a classical evolution by the exponential growth of uncertainty, a classical uncertainty. So in that sense, the quantum nature of the world should help you in a way. There is a decorrelation due to recollisions and another kind of decorrelation which should be due to the quantum fluctuations. So far, nobody knows how to do it, but morally, these two phenomena of decorrelation should pile onto each other and globally help you.
Thank you.
Yeah, so it's my turn. I'm getting another question related to Shannon's entropy. So it's coming from the audience. That E.T. James has a book titled Probability, the Logic of Science, where he has an opinionated discussion of the relation between Shannon information for discrete distributions and for continuous ones. And he suggests that the transition to the continuous case is not as trivial as is often assumed. Do you think this topic is worth thinking about carefully, or do you think it's rather a trivial matter?
I know the book. I have not read the book by James, but I know this issue. And I'm not sure. One first thing is worth mentioning, by the way, that Boltzmann himself was not at ease with the infinity concept in mathematics and thought that everything eventually was discrete and finite eventually. And that for him, the real world was finite, so to speak. So he may not have perceived or understood what is the kind of issue that is for us. I have worked on the continuous version of the large deviation problem, the Sanoff theorem, in which you use the Boltzmann entropy in the continuous world. And it's very technical, even though I did not see any major surprise in there. It is technical indeed. The work for Fisher information, going from the discretized version to the continuous version, is even more tricky. This is famous theory of large deviations by Donsker and Varadhan. Let me write you a formula. I don't know if it's the way that James presented it actually, but if you want to write a formula for H of F, there is one possible way. You take x1, etc., xn, id, random variables, and you look at the empirical distribution mu hat n, which is 1 over n sum of Dirac, xi. And you will test your empirical distribution and ask whether it's comparable to a certain fixed distribution that you're interested in. So you look at integral of phi f minus integral phi mu hat n, which is actually the empirical mean, 1 over n sum of phi of xi. You will ask whether that error is small, and you will do this for any test function phi. So there is a certain, these here x1, xn will be distributed according to G, and F is the profile that you're interested in. And so now you will ask the probability that this occurs, and you will ask the probability, that this occurs for any phi. You cannot really put just any phi, but let's say that you take an enumeration of all your possible phi's, phi 1, phi k, etc., for any phi j for j less than k. Phi 1, phi 2, etc. are all possible test functions that you enumerate in a dense countable basis. And then you will take the limit, and you will take the triple limit, actually, the limit in which first n goes to infinity, then k goes to infinity, then epsilon goes to 0, and then k goes to infinity. Okay, and when you do this, the result we obtain is integral f log f over g. This is true also in the continuous world, but you have to be careful at infinity, etc. I worked on this with my former student, François Bollet, and also with Arnaud Guillin, actually, one of these things. But this is an instance of the Sanoff theorem, and the issue is the continuous Sanoff theorem. There are 3 limits, and there's no way you can do without these 3 limits. Limit on number of particles or number of observations goes to infinity, limit of the error of the measurement goes to 0, and limit of the number of observables goes to infinity. Now, if you want to treat this, to treat the Fisher information, it's not far, but instead of having x1, xn distributing according to G, you will have instead, you will take xt to be solution of the stochastic equation associated with the distribution G, which is dxt square root of 2 dbt minus grad log G of xt. This is the yes. This is the stochastic process whose equilibrium value is exactly equal to G. And here you replace this 1 over n sum blah 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 by 1 over t integral phi of xt dt. So an empirical mean along the trajectory of the SDA. And then when you do this, you will obtain the relative Fisher information. It is integral of f grad log f over g square. So, epsilon goes to infinity, yes, and now is t goes to infinity. So, there is also in this way the three limits. This phi k. Okay. This is very difficult to find a reference. I put a student on this, as you know, some work to be trained, and you have to go through the works of Donsker and Varadan. It's okay. It's there, reformulated in a different way, a bit hidden in there. So this shows you a way to how to construct in the same kind of framework the Fisher information from this observation. And this is also continuous. And it's tricky to do it continuous, but it's continuous. I have not really answered the question because I haven't read the book of James carefully, but in my view, the going from the discrete to the continuous is technically tricky, but not so deep.
And I read somewhere that one can give a new proof of the central limit theorem using the H theory or the H theorem of Boltzmann.
Totally. This was done. This was a motivation, and it starts from the following observation, and this goes back to Linnik, Russian mathematician Linnik, and was developed. And the idea is this. If you take x and y, which are independent variable, IID, then h of x1, x plus y, over square root of 2 is less than half h of x plus h of y. Here I write h of x for the information of the law of x. Mm-hmm. So this is a particular case of the Shannon-Stam inequality. There is the same also with I, and then it's usually called the Blackman-Stam inequality. So taking the sum of independent random variables and divided by square root of 2 reduces the Boltzmann information. But that operation is the scaling of the central limit theorem, you know. You do x, etc. plus x to the power 2k divided by square root of 2k. Going along powers of 2 is doing this repeatedly, again and again and again, so it will lower and lower and lower. And the same operation will preserve the covariance matrix. So you are looking at H which goes down and down, but the covariance matrix is preserved, and the minimum for that is the Gaussian distribution. I like to think of it this way. Actually, along the central limit theorem, there is a loss of information, and so we are going to a distribution function which is more and more common, more and more difficult to reconstruct. That is a Gaussian one, the one with minimum h and minimum I.
Yeah. If we had a minus on h, then we would say that the Gaussian is the measure of maximal entropy, right? Would that
absolutely.
Yeah.
Absolutely.
Yeah, okay.
For the first 10 years in my career, I called 8 the entropy. And following, there is a use, mathematicians like to use convex functions, and Peter Lax had based his theory on compressible fluid dynamics on convex entropies, etc. And then one of my colleagues, Sasha Bobelev, convinced me that this was a sin, and that entropies are concave, and that entropies are increasing, not decreasing, and that I should reverse my convention. So if you read my papers up to 1999, I am working with entropies which are decreasing, and from that on, entropies which are increasing. This is just because I changed my convention.
Yeah. Okay, so Søren, your turn.
Thank you. There was another question. Let me quote. I read that, and now there's a quote in the question. If the existence of solutions to the Boltzmann equation is proven even far from equilibrium, their regularity and uniqueness remains a very important open question. That's the end of the quote. What does this mean? That was the first thing. And then additionally, what is now, given your new results, does that mean that this is a very important solved problem now that you...
The biggest, most central issue, maybe not the most famous in general for people, but for mathematicians working in it, the most important central issue is the regularity and smoothness of solutions of the Boltzmann equation. It's one of these big issues of regularities of partial differential equations, like there is the one for the incompressible Navier-Stokes, which is one of the Clay Millennium Prizes. But also there are the same for the compressible Navier-Stokes, which in my personal opinion is much more interesting, and also for a number of other equations from mathematical physics. And at the end of the 90s, my advisor Pierre-Louis Lyons, together with Ron DiPerna, proved the existence of very weak solutions for the Boltzmann equation. And this was hailed as a major success. It was a huge progress, but there was hope in those days that it would be a first step to study the regularity of the solutions. But no progress has been made since then, which made it that a number of people, including myself, consider these solutions as not relevant. And a solution, it depends on, for a PDE, there may be 10 different notions of solution. What is a solution is a key issue. And I consider that in this problem, the relevant solutions really should be smooth. And after we've gone through all possibilities of non-smoothness, etc., and I convinced myself that there has to be smooth and with exponential type decay, both because we don't see anything from the physical point of view suggesting, physical or mathematical point of view suggesting there should be a blow up or something, and secondly, because when it goes to the n goes to infinity limit, we badly need such estimates. The proof of Lanford uses decay which has Gaussian-like, actually fk, the marginal for k distribution should be, each of the marginals should be decaying like constant with a x squared plus v squared, something like this, Gaussian decay for the partial. I strongly believe in this, that there should be at decaying at least like fractional exponential. One of the big discoveries of the past 20 years, big theories, is to show that actually the global regularity of the solution boils down to just a few quantities. I mean, these kind of key quantities, so that if you can control them and you control the whole. And globally, what has been shown is that if you have a control on the density and temperature, just these two, and that there is no peak of density, no void, so density bounded from below, temperature bounded from, yes, I believe it's density bounded from below and temperature bounded from above, or maybe it's the reverse. But just these bounds on density and temperature are enough to prove the whole thing, that you have propagation of C-infinity, irregularity, etc., etc. And this was true in all solutions in which there was a good homogeneous series. So now, thanks to our result with Humbert and Sylvestre, it's also true for those very singular interactions. So globally, and this is a few, those say 20 or 30 papers together from the past 20 years. If you have the control on just the density and the temperature, then you have the global solution. I mean, pointwise density and pointwise temperature, then you have global regularity. And then it's this usual thing, as we say in math, then we need new ideas to tackle these two key bounds. At least these ones make the whole result kind of more plausible, if you see what I mean. This is for the equation without boundary. There may be issues, there are some subtle issues when it's boundaries and when it's a non-convex boundary. Then at the point of non-convexity, there is a whole issue of possible defect of regularity stemming in particular from the works of Yan Guo.
Thank you very much. Over to Karma again.
I think we might take just one or two more questions and then let Cédric get a bit of rest. So maybe just one or two more questions that you might choose. And
I just saw all the other questions. I was on the wrong page, but I have a question about Poincaré recurrence. Why doesn't the second law of thermodynamics or increase of entropy contradict? Why is there no contradiction with the Poincaré recurrence?
Oh, yeah, this is one of the usual issues. It's called indeed the Loschmidt paradox. There are two paradoxes, the Loschmidt paradox and the Zermelo paradox. One of these paradoxes is about the reversal of time and the other about the Poincaré recurrence theorem. Poincaré himself actually did not believe in the Boltzmann approach precisely for that. And this is one of the instances in which Poincaré was wrong. So while there is no contradiction, simply because the Boltzmann equation is infinite dimensional, and so you have an infinite number of balls. The Poincaré recurrence time goes to infinity as the number of particles increases, and it goes to infinity very fast. It's like an exponential, or exponential square maybe. And the number of particles is like 10 to the 20 or 10 to the 23 and so on. So the Poincaré recurrence time is out of this world. So there is one modelization in which you can fix the number n goes to infinity and you see as time goes to infinity, but the Poincaré recurrence time will never occur, just never. This universe will have long been gone before the Poincaré recurrence time is achieved for just a small box. So the Poincaré recurrence time is never occurred. And the Boltzmann situation, of course, is an approximation because the number of balls in the real life is finite, but very large. But actually approximate the Boltzmann equation from this, by this point of view, this large finite number by the infinite limit, n goes to infinity, is a better approximation than the Poincaré recurrence theorem. And this is what numerical simulations show and what is shown. So it's actually one of the motivations for having explicit estimates on the error that you do when n goes to infinity. This is like all this game of constructive bounds for the law of large numbers. And on this, it's very plausible. And when we understand the issue of the regularity of the Boltzmann equation, when you understand the approximation and so on, I saw in the chat somebody mentioned the BBG-KY hierarchy. Yes, BBG-KY hierarchy should also be a tool in this, even though I would prefer it if we would not need to use a BBG-KY hierarchy past the third rank for various reasons. But that is another discussion. But BBG-KY hierarchy is about studying the evolution of 2 particles, 3 particles, 4 particles, depending next round, etc., etc. So the error which is made as n goes to infinity should be relatively small, and this should be quantified. So the error can be measurable, and then we would say the infinite dimensional version is a good approximation of the real world, while the t goes to infinity at n fixed, like in the Poincaré recurrence time, is a bad approximation, something that will just never occur. For these Poincaré and Zermelo paradoxes, it's rather well explained in the books by Cerciniani. And it's funny that, well, the theorem, the paradoxes were there already more than 100 years ago. Boltzmann had to discuss this already in his time. Actually, the story of Boltzmann is tragic because he could not get his theory admitted in his lifetime, especially in Vienna, in which the school of the energetists was very powerful. He was at fierce battle and he was exhausted at the end of his life. He committed suicide eventually, just a few years before his theory became mainstream. That's one of the great tragedies of the history of sciences. And it's funny to see that these paradoxes related to the Zermelo-Loschmidt objections, etc., already in those days were still there. And nowadays we still have to think about them, and it requires, because these are deep paradoxes, and it's extremely deep even when you stay at the level of the classical mechanics.
Thank you. I think I'm done.
Thank you very
Thank you
much.
very much.
Thank you so much. I will leave the final word to Dr. Ayman, the president. But before that, I just want to share with you all, since Cédric, you mentioned Alain Aspect and others. Well, life is sometimes well made, because Alain Aspect will be delivering one of our Gaza Excellence talks on, as you can see, 22nd of October. And I'm very happy to take this opportunity to share our fall program with Edward Witten. We will have a short break over the vacation with Edward Witten, who's also a Fields Medallist, on 15th of September. Michel Mayer, who is a Nobel laureate, on 2nd of October. Alain Aspect, whom you mentioned, on 22nd of October. And Anne Huillier, who is a Nobel laureate in physics, so is Alain, as you can see, Alain Aspect, on 11th of November. So you see, we have a very beautiful, the Al-Aqsa University and us have a very beautiful program for this fall. And I will let the final word go to our wonderful partners, Al-Aqsa University. Dr.
Okay,
Ayman,
thank
if
you
you want
very
to-
much. Thank you very much, Dr. Christine. Thank you very much, Professor Villani, for this interesting lecture. I exceed my many thanks for all participants. As a mathematician, it was, as a mathematician also, it was very valuable discussion with Professor Villani. We are happy that Professor Villani will be giving his lecture through the university official website. I hope this lecture will be held at Al-Aqsa University in Gaza soon. Christine, Saida, all participants, thank you very much. Thanks, Christine, for your clear efforts in holding these lectures. We look forward to seeing you in more lectures at Al-Aqsa University. Thank you.
Thank you so much. We will indeed soon be physically at Al-Aqsa University to deliver these talks. Cedric,
hope so.
thank you so much. Thank you very much, Cedric. Thank you to all the attendees. Tusen tack, and thank you so much, Karma. And we will be, this talk will be uploaded on our YouTube channel, but I will email it to you so you can watch again and voila, and watch Villani's charismatic talk again. Thanks, Saida, and thank you, Dr. Hazem. Thank you, Dr. Ahmad. We will see you very soon.
Thank
Bye.
you.
Bye-bye. Thank you very much.
Bye.